Hey, welcome back, friends. So we're going to continue our hypothesis testing and look at hypothesis tests for the mean. So in this situation, there's going to be a claim made about some population mean. We're going to test it in much the same spirit. We'll have to satisfy our normality conditions or use the central limit theorem. And then essentially play that same game of, mathematicizing the claim, placing it in the appropriate hypothesis, establishing our regions, our fail to reject and rejection regions based on the level of significance. And of course, that boundary will be determined by the critical Z, or in this case, T value. We then get our test statistic from our sample, find what region that lies in. That tells us what to do with the null hypothesis. And then that last step, always reinterpreting our decision within the context of the claim. So let's go ahead and get started. We will need we will need our calculators as well. So if you want to get those going, I'm going to get mine out here as well. All right. So hypothesis testing for the mean. First situation, which is really the more common situation, if we don't know sigma, if sigma is not known, okay, then we need normally distributed population or n greater than 30. Okay? There's what our test statistic will look like. And then if we do know sigma, then of course we'll be using z's, okay? So t-scores if we don't know sigma, z-scores if we do, all right? But other than that, the process is the same. Again, these individual formulas change, but the big picture is the same. We need that critical value. We need a standardized test statistic to compare to the critical value, and then we can make a decision regarding the null. So here's a fairly common study, pretty well known. We generally accept that humans have a mean body temperature of 98.6 degrees Fahrenheit. University of Maryland researchers took the temperatures of 106 individuals. The result was a sample mean of 98.2 degrees Fahrenheit. Assume a population standard deviation of 0.62. Test the claim that the mean temperature is 98.6 degrees Fahrenheit at 0.05 level of significance. So first of all, let's see what we have here. I want to point out a couple things. First is that we know the population standard deviation, okay? Come back in here and do this again. We know the population standard deviation, okay? So we are given sigma, all right? N is indeed greater than 30. And so we have this Z, standardized Z distribution, right? Okay, so let's go through with all of our steps. Okay, the claim, right? We start with the claim. Well, the claim is that mean body temperature is, so equals 98.6 degrees Fahrenheit. All right, I've got my claim. I place it in the appropriate hypothesis. Notice that my claim contains equality. In fact, it is a statement of equality. And so I know where it will be placed in the null, okay? Now, that means the alternative, being the complement of the null, will be not equal to 98.6. All right, now, we know our alpha. What else do we know? Well, we know that this is two-tailed because our alternative is not equal, right? And so I can come in here and find my two critical values. Okay. Now 0.05 level of significance, remember that under that level of significance with two tails, there's going to be 0.025 in that tail and 0.025 in that tail. Okay. So let's go get our critical Z's. Okay. And of course you can do that with inverse norm. So second vars, inverse norm, 0.025. That's going to give me that lower value. So negative 1.96. Negative 1.96, and of course a positive 1.96. Don't forget, this is our fail to reject the null region. Okay, well, now we go find our Z, right? Something to compare with those critical values. Well, we're told we have this, right? So let's take a look. Our sample mean, right? When those 106 individuals were, when the temperatures were measured, turned out the mean was 98.2. Minus our claim of 98.6, all divided by 0.62 over the square root of 106. Okay? And so we do that. 98.2 minus 98.6 divided by parentheses 0.62 divided by the square root of 106. Okay. Get negative 6.64. Which is in big time rejection region, right? Like horribly reject, fantastically reject. So we're going to reject HO. Now we're at that point where we make our statement, okay? So at alpha equals 0.05, there is, well, this is where we need to ask, which of those two hypotheses was our claim? Well, our claim was the null. So if I'm rejecting the null, I am rejecting the claim. So we would say there is so we'd say there is sufficient or enough evidence to reject the claim that mean body temp is 98.6 degrees Fahrenheit. Okay? There we go. Hey, I wonder if our calculators will do this for us. Of course it will. So, stat. Tests. First one you see here, z-test. Well, if I had raw data, I could put the raw data in, but here I don't have the raw data, I just have the summary statistics. So we're making a claim that the mean is 98.6. Sigma is 0.62. The X bar that came from the study was 98.2. Our sample size was 106. And our null hypothesis is not equal. Come down here to calculate. There we have it. Okay. So, right, it tells you this Z here, just like we got. By the way, it also gives you a P, right? You can compare with alpha. I don't want you to forget that, right? This P is much less than alpha, okay? Well, than alpha over 2, I guess I should say. So you're going to reject that hypothesis on those grounds as well, right? And they should agree. Just remember, either method works. I just like the critical value method. All right, let's try another one. Health Club. Whoops. Where am I? Here we go. A health club claims that after only 2 days of their new program, participants will lose weight. It's a pretty easy claim to make. Yeah, right. You work out for a couple days, you'll probably see some loss in water weight. Doesn't mean the program is working. Let's see. A random sample of 33 participants yielded a mean weight loss of 0.37 pounds and a standard deviation of 0.98 pounds. Test the claim at 0.05 level of significance. All right. So, sigma is unknown. You want to be careful because you might be saying, but wait, it says standard deviation. Yeah, but where did it come from? A random sample of 33 participants, okay? Sigma is unknown. N is greater than 30, right? And so I'm going to use the t distribution, okay? Now, the claim, if you are measuring weight loss, then you should see a positive amount of loss, right? The amount of weight you've lost should be greater than 0. So the claim is that the mean is greater than 0. Again, we're talking about weight loss. So you're quantifying in a positive way the amount of weight that you've lost. Well, let's see here. HO and HA. My claim does not include any statement of equality. It's a strict inequality. So it goes in the alternative. Therefore, my null is mu is less than or equal to 0. And of course, you could just think of that as equal in order to be most conservative, but it's up to you how you want to articulate that. All right, so let's see. This is right-tailed. And alpha is again 0.05. And so that area is 0.05. Here is our fail to reject region. That's HO. Sorry, guys. And so we want this critical T value. Again, we're talking about T because we don't know sigma. All right. Well, let's go find T. Now you could go to your chart and use degrees of freedom, right? Degrees of freedom would be 32. Or we can do second distribution, inverse T, got the 84 here. And then the area will be 0.95. The degrees of freedom will be 32. So 1.694. Okay. All right, now we go get our standardized test statistic. So T equals, well, mean weight loss of 0.37 minus 0 over 0.98 divided by the square root of 33. Okay. So 0.37 divided by 0.98 over the square root of 33. 2.169 if I'm rounding. And so this T is definitely in my rejection region. Reject the null. So at alpha equals 0.05, there is sufficient evidence to, well, to what? We've rejected the null. The null is the complement of the alternative, which is our claim. So if we are saying the complement of our claim we can reject, that tells us we should accept the claim, right? Of course, there's a 5% chance we're wrong, but shoot, those are pretty good odds. So at alpha equals 0.05, there is sufficient evidence to support the claim. Uh-oh, what just happened? Sorry, I just lost my notes here. To support the claim that participants will lose weight after 2 days, okay? And again, remember, of course they're gonna lose weight. This test would be more meaningful if you did it after what, 6 months, a year? You can see this done all the time, right? Misleading, you know, you perform a test, and you get a statistically valid result, but stop and ask if the setup or the choice of when to perform the test is relevant or not. So, all right, let's look at one more here. Company claims that a bottle of cola has 40 milligrams of caffeine. You test a random sample of bottles, 31 of them, and find a mean caffeine content of 39.2 milligrams with a standard deviation of 7.5 milligrams. Test the claim at 0.01 significance. And so this is really important because what you have, right, are you have a label that goes on these bottles, whether it's soda or wine or beer or iced tea or even water, whatever it is. There's a label that goes on the product that says the contents. So if they're going to tell you there's 40 milligrams of caffeine, they need to make sure that their bottles actually contain 40 milligrams of caffeine. Now, we know from continuous data that the probability of any bottle actually having exactly 40 milligrams is 0. So the issue really is, on average, 40 milligrams. And there's a secondary issue too, which we're not going to get into, but and that is having a small standard deviation, right? It would be fine. I could have a bottle with 20 milligrams of caffeine. I could have a bottle with 60 milligrams of caffeine. The average is 40, but what a big spread, right? So when people that are in quality control want to also make sure that the variation between the bottles' caffeine contents is very, very small. So there's actually 2 pieces that someone in quality control will be concerned with: the average or mean content, as well as controlling for a very small variation. We're going to focus just on the mean here. So the company is making the claim that their product has 40 milligrams of caffeine. There's our claim. It's been mathematicized. Let's place it. The claim includes a statement of equality. So it is going to go in my null. So there is my alternative, not equal. Now sigma is unknown. N is greater than 30, barely. So we have the t distribution. All right, 0.01 significance, 2 tailed. So the area in each of these, 0.005, 0.005, and here is our fail to reject H naught, or the null. All right, let's go get our t value. Whoops. So inverse t. That area, I'm going to get the negative one, is 0.005. My degrees of freedom, 30, right? Because my sample size, or was my sample size? Sample size was 31. And then we paste. So negative 2.75. Negative 2.75. And over here, positive 2.75. Okay. Well, let's go get our t value now. Now, in the last example, we used the formula, right? Well, watch this. Let's go back to our calculator. We have a t-test. Check this out. Stat, tests, number 2, t-test. There we have it. So the stats, mu0, right? The claim is that there are 40 milligrams of caffeine. The mean from our sample is 39.2. Notice that it's not asking for sigma, it's asking for S, right? Because the calculator knows that a t-test is when you're given a sample but don't know the population standard deviation. So let's go see, what do we have? 7.5. Our sample size is 31. Is that right? 31? Yep. And our null is not equal. So there we go. T is negative 0.594. Negative 0.594. So fail to reject the null. Okay. Which is good if you're the company, right? That says there's not enough evidence to tell us we're wrong. So at alpha equals 0.01, there is insufficient evidence to reject the claim that the mean caffeine content is 40 milligrams. All right, so there we have it. We have hypothesis tested for the mean. Much like confidence intervals, we have the two cases, right? Whether or not we know sigma. If we know sigma, we're going to use the z distribution. If we don't, we're going to use t. Of course, we have to make sure the conditions hold, namely either the populations we know are normal to begin with, or our sample size is greater than 30. Other than that, the process should feel very similar, right? Whether it was proportions or means, you had this process. You mathematicize the claim, you place it in the appropriate hypothesis, you set up your distribution with the rejection and fail to reject regions clearly identified. You then find your test statistic and figure out which region it falls in. You make a decision about the null, and then you reinterpret in the original context of the claim. Once that is done, you have completed the hypothesis test. I want to finish with just one comment about that contextualization. I believe that's the hardest part. But hopefully, as you think about this, you're starting to see some commonalities come through. Namely, if your null hypothesis is the claim, or let me word it this way, if your claim sits in your null hypothesis, then your language is going to be about rejection. Sufficient or insufficient evidence to reject, right? Because if you're testing the claim, or if you're testing the null, and the null is the claim, then you're actually testing the claim. However, if your null is in the alternative, then rejecting the claim is actually supporting the alternative. I'm sorry, I said that wrong. If your claim is in the alternative, then rejecting the null is a support of your claim, right? Because you're saying, hey, everything that's not my claim is probably false. So if everything else is probably false, and these two things are complementary, then this thing here must be true. And I say must be, it's obviously there's that alpha, right? And it says I might be wrong, but it's a small chance. Similarly, if you can't reject the null, then an alternative hypothesis as your claim is not being supported, right? The only way for the alternative to be true is if the null is false. And it's the null that's getting directly tested. So when the claim is in the null, our statement involves some language of rejection. When the statement, or when the claim is in the alternative, our contextualized statement involves some language of support. Okay, all righty. Work back through this, make it your own. I hope things are going well for you, and I will talk to you guys soon. Bye-bye.